Hi, this is Mark Weitzman. Welcome back to Quantum Field Theory, a Student's Perspective. And I'd like to continue with our Lesson 3. With our Lesson 3 on canonical quantization of scalar fields. Today we're doing the third 3A in our videos. I'll explain the A shortly. So in this third video, which I'm going to cut into two pieces, we're going to do the canonical approach, which is a more mechanical approach. And this particular video will be sort of like a review tutorial. So in the previous video, we did a physical bottom-up approach. And in this video, we're going to do the canonical approach. And this is like a top-down. And it's a more mechanical procedure. We will end up in the same place. But there are advantages to the canonical approach. We will find that it's easier to add interactions. Now, we're a long way from adding interactions, but eventually we're going to want to add interactions, and so we'll find the canonical approach is the way to go. So following Coleman's approach, we illustrate the what he calls method of the missing box. So let me draw 4 boxes. So in this box, we're going to we have classical particle mechanics. And in this box, we have classical field theory. And in this box, we have quantum particle mechanics. And let me erase this. Just draw it with dotted, because this is what we don't have, and we call this quantum field theory, the holy grail of life itself. So the idea is we're familiar with classical particle mechanics, and one of the reasons why I call this a review tutorial is that I'll review it very quickly, but we're assuming you're familiar with this. And the same thing, we assume you're familiar with quantum mechanics. And classical field theory you're probably also familiar with. I'm sure you've all studied Maxwell's equations and everything. But you might be a little bit less familiar with classical field theory. And then we could go this way, or we could go this way. When we go this way, we're taking the continuum limit when we go this way, we're doing what's called canonical quantization. So we could first go from classical particle mechanics to a continuous classical field theory, and then apply canonical quantization, or we could go from classical particles to our beloved quantum mechanics, and then go to the continuum limit. So we have two ways to go, and I want to cover in this video, video A, 3A. I want to cover all boxes except QFT. Next video, 3B, we'll do the QFT box. So let's start with classical particle mechanics. Okay, so I'm going to take a little bit higher level approach than starting with Newton's laws, because I'm sure you've all taken hopefully you've all taken an advanced quantum mechanics course. You know, I'll give a reference here. Goldstein, Landau, and Lifshitz. I'm sure I misspelled his name. Either one is excellent. Okay, so we have dynamical variables. Dynamical variables, we always mean variables that change with time. So I'll call these Q. And the reason why I'm using Q rather than X is because when we do classical field theory and quantum field theory, X will refer to space-time. Here these are any kind of dynamical variables. We'll index them by A because we may have more than one. They're a function of time. Let's say we have n classical dynamical variables. And then with these variables, we form a Lagrangian, which is a function of the variables and their derivatives. And we'll do time derivatives with dots. And it's not that the Lagrangian can't be a function of second derivatives or third derivatives, etc. It just leads to more complicated equations and hasn't really found much use in physics, so we'll keep it simple. Our action, which is a functional, and later in this course we'll talk about functionals. Just briefly, a function maps, let's say, a real variable x, or let's say a complex variable x, into another complex variable x. But a functional maps a whole function of x. I'm going to leave out the argument x. It maps the whole software. It maps the whole function to a number. Let's call this f of f, which is an element of C. And the best example of this would be like an integral. Let's say we have an integral from minus infinity to infinity of f of x dx. That's some number. So we're mapping all kinds of functions. We can have x squared, x cubed, square root of x. Anything that converges, we map and we get a number. So the function f literally goes to the number. This is a function, and this is a number. And later on, when we discuss the path integral approach to quantum mechanics, this will be very important. But I just want to cover this very briefly. So the action S is equal to the integral from t1 to t2 of the Lagrangian. And it could be an explicit function of time. Now, as you might remember, Hamilton's principle. Nowadays we refer to it as the principle of least action. I'll put this in quotes. The reason why I put least in quotes is because it's just an extrema. It could be a maximum, it could be a minimum, or it could be a saddle point. So it's just saying that something is zero. And what we do is when we say that we imagine making a change in our dynamical variables, this is at each point in time we change the value, except at the beginning and end points of the integral. So del QA at T1 equal del QA at T2 equals 0. And under this transformation, we need to have del S equal to 0. So that's Hamilton's principle. And now let's let's calculate it. So del S is equal to the integral from, and if for some reason you're unfamiliar with any of this, I recommend There's a chapter in one of the chapters in the Feynman lectures on physics on the principle of least action, and it's a basically it's a verbatim lecture by Feynman, who's his favorite topic in physics was the principle of least action. That's where he did his most profound work, and it led to his Feynman diagrams and path integral and everything else significant that he did was always sort of came back to the principle of least action. So we have del S is the integral from t1 to t2 dt. So I'm working with this, and I'm going to vary. I'm going to just use normal calculus. Okay, and this is equal to, now we just use the standard integration by parts. So all we did was we took this part because del q dot A is equal to, if you think about it, you'll see, del QA. So what we're doing is we're taking like u dv is equal to the integral of u times v minus the integral of v du. Okay. And this term over here is equal to 0 because del QA at T2 is equal to 0 and del QA at T1 equals 0. So this evaluates to 0. We can get rid of it. Now we have this expression, but this has to hold for every possible variation of the, so I should have said for all del QA which satisfying that. So the only way this can be 0, the whole thing can be equal to 0 for all del QA, is for the thing in brackets to vanish. So now we get the Euler Lagrange equations of motion. Partial of L with respect to QA minus So to illustrate this for the simplest case, classically, we have L is equal to T minus V is equal to 1/2 m. Let's say we're working in one dimension, x dot squared minus V of x. T is kinetic energy, V is potential energy. And then our variable, dynamical variable, is x of t. The partial of L with respect to x is equal to minus the partial of V with respect to x. And then I have minus d dt, the partial of L with respect to x dot, which is mx dot. This is equal to 0. So this equation is the same thing as mx double dot is equal to, put this on this side, is equal to minus the partial of v with respect to x. The partial v with respect, minus the partial v with respect to x is defined as the force. And this is mass times acceleration. So we get Newton's second law. Okay. We define, in general, we define the canonical momentum as the partial of L with respect to Q dot A. And do not assume that it's the same as what you're used to as the momentum. Sometimes in electromagnetism especially, I'll just put it on the side, like in EM, when you work with the Lagrangian, you'll find that the conjugate momentum is pi is equal to P minus Q. I'll put P minus EA, where E is the charge of the particle. And so it's not just P. There's sometimes corrections to the canonical momentum depending on the Lagrangian. So we form the Hamiltonian. This is defined as PA Q dot A. Now you might notice I'm putting indices up and down all over the place. They really have no relevance, but I'm always using the Einstein summation convention. And if you use the Einstein summation convention, you always want one up and one down. So, and also notice, like when you have an up index in the denominator, you might as well just write it as a down index on the variable. But for now, we're working in Euclidean space-time or whatever. None of this matters. It will matter when we start working with Lorentz invariant Lagrangians, minus L. So this is the Hamiltonian. And and the way to get Hamilton's equations of motion is we eventually we're going to change variables from Q and Q dot. We're eventually going to go to change our independent variables to QA and PA. But right now we'll say del H is equal to Q dot A del PA plus, we're just working off this, plus PA del Q dot A minus the partial of L with respect to QA del QA minus the partial of L with respect to Q dot A del Q dot A. So we're just using our standard taking total derivatives, using partial derivatives. The independent variables are still on this side over here. Now we can use the Lagrangian equations of motion. This term and this term cancel. because PA, remember I defined it, right here, PA is the partial of L with respect to Q dot A. So these two terms cancel, and we're left with these two terms. But we also have, once we, and you could see that in this case, our variables, the only ones we have left are like del QA and del PA. So we've made the switch to here. And let me make this a little brighter, the dots. Okay. So del H, just in general, since we have H as some kind of function of QA and PA, we would say del H is the partial of H with respect to PA, del PA, plus the partial of H with respect to QA, del QA. Okay. So now equating these two expressions, we can see that this has to be equal to that, and this has to be equal to that. So we get Hamilton's equations of motions. I want to box the important equations. I don't think I should have boxed that. And we get Q dot A is equal to the partial of H with respect to PA, and P dot A is equal to minus the partial of H with respect to QA. So that's it for classical particle mechanics. I'm not going to do any examples. You've probably done them ad nauseum in your undergraduate courses. Let's go to quantum mechanics, and I'm calling them quantum particle mechanics just to emphasize that we're doing normal quantum mechanics of one or finite number of particles. I want to, I probably should do this over here. We also define what we call classical, and this wasn't used that much. I mean, it was used a little bit. Classical Poisson brackets. Define that by F comma G is equal to, and I'll explicitly show the sum, but the Einstein summation convention would apply here. This is just a definition. And using this definition, if you apply them to the variables themselves, you get these very important relations. QA, QB, I'm sorry. QA, QB is equal to 0. PA, PB is equal to 0. And the one that's significant now, looking at this, you might say they seem very much like the commutators in quantum mechanics. And that would be correct. When Dirac was thinking about all this stuff, he had the idea that he wanted some kind of correspondence principle which would lead to classical mechanics, and he had the idea of replacing Poisson brackets with commutators. So we don't see the Poisson brackets much today, but you could see they're very similar to the classical, to the quantum commutators. Now let me go to quantum particle mechanics. So basically in QM, the canonical approach is to replace Poisson brackets by commutators. So we have the commutator. This is like called promoting variables to quantum variables. And whenever we do commutators, here I'm using these variables because they have time in them. These are Heisenberg time dependent variables. And we always impose, let me write down the last commutator, the one that makes a difference. So it's almost the same as this, except we have an I in here. And these are equal time commutation relations. And of course, I assume everybody in here knows that the commutator is defined by AB minus BA. Okay. So to get the new Hamiltonian, we substitute in the classical H, whatever variables we have, and now we're going to have these commutation relations. But as some of you know, I won't go into this here, there are factor ordering problems. If you have something like xp classically, what is it quantum mechanically? Is it xp? Is it px? Is it 1/2 xp plus px? This would be the choice in this case. We want something that's Hermitian and symmetric. But sometimes when you have things like x, p squared, x cubed, p to the fourth, x, whatever. If you have some crazy thing, you're going to get these factor ordering problems. And there's no way canonically to decide what's the right expression. Something you have to basically determine by experiment. Okay, So the equations of motion in quantum mechanics, in the Heisenberg picture, I'm not going to derive this again, but I think most of you have seen this. You know, if A is a time-dependent operator in the Heisenberg picture, the time dependence is given by the commutation with the Hamiltonian. Then there's also, if it has explicit time dependence, there's also another term. So let's just see what this leads to if we substitute just our basic variables. For instance, if we have dqa dt is equal to I h comma qa, there's no explicit time dependence in our variable here. And now this is going to be equal to I. Now, to satisfy these commutation relations, as many of you may know, we can work in a representation. You know, we can always sort of like, in evaluating commutators, we can do P equal minus IH bar the partial with respect to Q, or we can go Q equals IH bar the partial with respect to P. So here I have I times minus I. If I put a minus sign here, I'm going to have QA and H. Then QA then becomes the partial with respect to P. So this becomes minus I, the partial of H with respect to PA is equal to the partial of H with respect to PA. And dPA dt is equal to I H comma PA. Now this is going to be I times the partial of H with respect to QA is equal to minus the partial of H with respect to QA. So these two equations are the same, and that's the design. They look the same as the classical equations. So the quantum equations are the same as the Hamilton's equations. The Heisenberg equations of motion, Heisenberg are the same as the Hamilton. So that's nice. That's where the correspondence principle comes from. Okay. So that's our lightning review of quantum mechanics. Again, I'm not going to do any examples. Now let's have a little review of classical field theory. So CFT, that's a bad abbreviation, because it also stands for conformal field theory, beyond the scope of this course. So classical field theory is just classical particle mechanics with an infinite number of degrees of freedom. Now, although I'll start using a continuum mode description, it doesn't have to be continuum. We could work with Fourier modes, but either way we're going to get an infinite number of degrees of freedom. That's what distinguishes them. And the correspondence, the thing you should keep in mind is that a classical degree of freedom, described by a finite number, the index A, essentially goes into a field. The number of fields also could be described like n fields, but we have this additional variable, which is usually space. That gives us our infinite degrees of freedom. It's like we have a classical variable at each point of space. Time is the same as time. And the index A, which before was just finite, sort of goes to two indices right now. It goes to a finite number of fields, but also a continuous or an infinite number of positions. Now, to make things easier, it's easiest if we treat space and time the same. That's the easiest way to get a Lorentz invariant theory. There are other classical theories like in elasticity and everything where we consider Coulomb forces between atoms that are non-local. So you don't have to have Lorentz invariant theories in physics, but for our purposes that's what we want to restrict ourselves to. So we're going to restrict to Lorentz invariant theories. And we'll do this by defining a Lagrangian as being the space integral of a Lagrangian density. So we're going to integrate over all space. This is called the Lagrangian density technically. But you'll find in most field theory books that they'll just refer to it often as the Lagrangian. So don't let that freak you out. So what we have is L is equal to the integral d3x, the Lagrangian density. It's a function of the fields. It's a function of the derivatives of the fields. And sometimes it's a functional of space-time itself. So we're going to tend not to use that much, but sometimes we'll have external fields and then we'll use it. The action again is defined by the integral from t1 to t2 of the Lagrangian, which now works out to the integral of d4x L of Vax partial mu Vax comma x, and just to make sure time is restricted still. Okay. Now we're going to parallel exactly what we did in the classical case, and we'll derive the Euler-Lagrange equations of motion. Zero is equal to del S is equal to the integral of d4x and if you haven't seen this before, I suggest you look in the last chapter of Goldstein where he covers field theories, just to make yourself more comfortable with this. But really it's a minor extension. And I'm going to point out, you can easily verify in the same thing as the other case, del mu phi a is equal to the and we also have that the fields satisfy the following conditions. All over space, but at T1, there's going to be no variation in the fields. Just same thing as we did before. And we're going to also have that for all times, at infinity, at any time, any variations are 0. Actually, the fields themselves so we're assuming that the fields fall off sufficiently fast so that at infinity they're 0 for all time. Now, obviously, when we do things like incoming electromagnetic waves and everything, this condition can't really hold. But in deriving the Euler-Lagrange equations of motions, we always assume this. Okay. So going from here, we use our usual integration by parts. So this is equal to the integral d4x A here. And this has to hold for all variations of del phi A. All. Satisfy those conditions. You can see when we have a time derivative, it vanishes because at T2 and T1, the variation is 0. When we have a space derivative, it vanishes because the fields themselves vanish at infinity. So there's no boundary term. Okay, so we end up getting our equations. And again, in case you're not that familiar with the notation, A is just like which field. We could be working with one field, in which case we wouldn't have an A. But we could be working with several fields. Electromagnetic field, we might have 4 vector potential and scalar potential fields, or if we're working with the fields directly, we might have 6 electromagnetic fields. But we could be working with a Klein-Gordon field, scalar, real, and then just have one field. Mu, of course, is always a space-time index. Okay, so let me box this. Now, Coleman defines, not all books use this, but Coleman defines pi a mu so it's this term in here he defines as pi mu a. But really the one that's important is pi 0a, often just defined as pi a, and this is equal to the partial, in other words, the time one of this partial L with respect to theta. So keep that definition in mind. This is called the canonical momentum density. But again, remember that a lot of times they'll just say the canonical momentum. Okay. The Hamiltonian density is defined in the same way as in classical particle mechanics. Pi a phi dot a minus L. And the Hamiltonian is defined the same way. So again, H is the Hamiltonian density. The non-script H is the Hamiltonian. And that's that. Now, let me just do one simple case for which we'll need. So to illustrate this classical field theory. So a single real scalar field will define a Lagrangian as 1/2. We want Lorentz covariance, and basically this is going to be the only one that works. To get a something covariant out of a scalar field, the simplest choices are to square it, or we could take the derivatives and take a dot product of derivatives. This is the simplest choice. M squared is just a positive parameter for now. We'll relate it to the mass later. And the 1/2 is conventional. Okay. Now if you were to write this out in non-covariant notation, sometimes that's easier to see what's going on. It's 1/2 v dot squared minus the gradient squared minus m squared v squared. So to get the Euler-Lagrange equations of motion, we take the partial of L with respect to phi, which is equal to minus m squared phi. And then we take the minus the partial of mu. We take, let's look over here. You could see that you're going to get a factor of 2. You could take this one and then times that, or that one times that. So you're going to end up getting partial of mu phi as that term. If I go back to the partial of mu I put there, the partial of L with respect to the partial of mu phi, mu is going to just go upstairs there. This is equal to 0. We can rewrite this. Coleman uses a funny notation, box squared phi, if you take away the negative signs. Most other people, just use box equal partial mu. Coleman uses box squared. And where we get box squared phi plus m squared phi equals 0. And this is the Klein-Gordon equation. Now there's a very simple approach. If we're given the equation and you want to find the Lagrangian, I'll have an example in that later on in one of the problems that I'll do at the end of the videos in this sequence, where we'll do it for a vector field to show you how you can go from the equations of motion to the Lagrangian. It's very trivial to work backwards. The canonical momentum is defined by the partial of L with respect to phi dot. So using this version, this is just equal to phi dot. And now the Hamiltonian density is equal to pi times phi dot minus L. This is equal to pi squared minus 1/2. Remember, phi dot is equal to pi, so we can make that pi squared minus del phi minus m squared phi squared. So this is equal to 1/2 pi squared del phi squared plus m squared phi squared. As you can see, it's positive definite. All the terms here are positive, so it doesn't matter if we have a large gradient or anything. That sort of determines the sign in our original Lagrangian. If you put a plus here instead, you're going to end up getting a minus there, and that's going to be a problem. Okay, and the actual Hamiltonian is equal to 1/2 the integral of d3x pi squared I'm not sure why they use this absolute value notation. I would just say del phi dot del phi, but it seems most of the books use it. I guess it would be, when it's complex, it would be del phi star dot del phi. Maybe that's why they use it. Plus m squared phi. So this is our Hamiltonian. Our Hamiltonian density. Okay. Now, the Hamilton in complete analogy, with classical particle mechanics, we're going to have phi dot is equal to, I'm going to write functional derivatives here and explain why in a second, because we're going to need this. But I'm also going to call this like the partial of the density with respect to pi. And pi dot minus del h del phi, and I'll just call this like minus the partial of h with respect to phi. So let's verify these. So we can start phi dot is equal to the partial of h with respect to pi. This is equal to pi, so that's good. That's what we had before. That's what got us started. That's consistent. When we went from the Lagrangian, when we defined pi over here in this equation, so that's consistent. And now let's get the second equation. Pi dot is equal to minus del h del phi. Now here, because of the gradient term, it's not exactly obvious how to handle it in terms of partial derivatives. That's why I want to use the technically correct functional derivative, and I'll explain in a second what that is. So here I'm using the Hamiltonian, not the Hamiltonian density. So let's see how this works. Let's write h is equal to the integral of d3y, and let's just do the term that bothers us. The other terms will be very easy. Dot del phi y. Okay, so now let's take a functional derivative of this. And when we take a functional derivative, we take it at a specific point. That's why I have this x here. It's the field at a specific point. And what this becomes is the integral of d3y and I can move that functional derivative through the delta thing there. So this is like standard manipulations of calculus, except for one thing. And that is, you have to know this basic rule that for functional derivatives, del phi y, del phi x is equal to delta, the delta, usual delta function. I'll write it with a 3. And as I said, when we do path integrals, we'll review all these rules. So this is going to be equal to, both these terms are the same, 2 times the integral of d3y del, this is the gradient, this is the three-dimensional delta function, now we can do integration by parts. And now we just do the usual evaluation with the delta function. So this is equal to minus 2 del squared phi of x. Okay. So our equations of motion becomes pi dot equal minus the functional derivative of the Hamiltonian with respect to the field. It's equal to minus. And now I'm going to get, remember there's a half in front of this term I left out. I should have a half here, but I get minus del squared phi. And then the other term, when we take the derivative, like I said, this is no problem. This is a completely independent variable. And this is, I left out the phi squared here. Sorry. When you take the derivative of this with respect to phi, it's obviously 2m squared phi times a half. So this just becomes m squared phi. Remember, pi is phi dot, so this equation is just phi double dot equal del squared phi minus m squared phi, or phi double dot minus del squared phi plus m squared phi equals 0. And that's the Klein-Gordon equation again. Okay, so that does it for this long half of a lecture, this 3A. When we come back, we'll do the quantum, and in the quantum we'll, because the equations of motion, the Klein-Gordon equation, is linear, we can solve it by like Fourier transforms, and we'll expand the field in terms of creation and annihilation operators. And since we have the commutation relations for the field, we can invert them and get the creation and annihilation operators in terms of the fields, and thus get their commutation relations. And then we get the same interpretation of Fock space and everything. So we end up back in the same place. And I'll do that in the next lecture. Thank you very much.